Hello and welcome to this new video series on numerical methods for solving partial differential equations or PDEs. Unlike ordinary differential equations, PDEs involve functions of multiple variables and partial derivatives with respect to each variable, therefore describing multidimensional processes. Here t, x, and y are independent variables, which often represents time and space. U is the dependent variable. The dimension of PDE is the number of independent spatial variables, which in this case is 2. And the order of PDE is the order of its highest derivative. Second order linear PDEs are typically classified into elliptic, parabolic, and hyperbolic types. For a second order linear PDE with two independent variables, we can use the discriminant of the second order part to classify the PDE into elliptic, parabolic, and hyperbolic types. The examples of elliptic PDEs are Laplace and Poisson's equations. We can see that both A and C are equal to 1, whereas B is equal to 0, which means the discriminant is minus 4 and less than 0. An example of parabolic PDE is one-dimensional heat or diffusion equation. In this case, both A and B are 0, whereas C is equal to negative of thermal diffusivity. This means that the resulting discriminant value is 0. An example of hyperbolic PDE is one-dimensional wave equation. Here A is equal to 1, B is equal to 0, and C is equal to negative of the squared wave speed. This yields a discriminant value which is equal to 4 times the squared wave speed, which means the discriminant is greater than 0. For a second order PDE with more than two independent variables, we can look at the eigenvalues of the n by n coefficient matrix of the second order terms to classify the PDE into elliptic, parabolic, and hyperbolic types. Let's look at an example of two-dimensional wave equation. The coefficient matrix A in this case only contains diagonal elements. We know that the eigenvalues of a diagonal matrix are the diagonal elements themselves. But let's quickly look at the process of getting the eigenvalues of a 3 by 3 matrix. For this, we solve the characteristic equation, which is determinant of A minus lambda I equals to 0. Solving the determinant yields this equation, which gives the same results as the diagonal elements in matrix A. In this case, all eigenvalues are non-zero and one of them has the opposite sign of the remaining two, which tells us that the wave equation is a hyperbolic PDE. This concludes our video. In the next video, we will use explicit finite difference scheme to solve a one-dimensional heat equation example. Please subscribe to my channel. Thanks for watching and see you in the next video.